Welcome to chapter 23, amines, and then we'll finish up with the amino acids classification in chapter 27. This question, what is the major organic product in the reaction below? So this was a review. This is the aldol reaction. So remember that we have our alpha hydrogen here, and we make an enolate. And then you draw another ketone, and the other ketone is the electrophile. And then when you draw this together, we draw the alpha compound just like it is, and then this beta carbon here undergoes nucleophilic acyl addition, and then it picks up the proton, and so you get the beta hydroxyl. There's alpha, beta hydroxy, carbonyl. Now, because you're still in sodium hydroxide, this alpha hydrogen is very acidic, so it's going to undergo the E1CB mechanism, which is, this is the E1, which is unimolecular elimination, and then CB is the elimination of the OH to make the alpha beta unsaturated compound. Now, the thing is here though, you can count your carbons, so that's 6, 7, 8 carbons, so there's going to be 16 carbons total, and you can see that this one, here's your alpha beta, but you're missing a methyl group. This is not right. This one's also the alpha beta unsaturated, but it's missing the methyl group. This one has the methyl group, so if you count that, that's 16 carbons. So in this product, we have stopped at the beta hydroxycarbonyl. All right, so we are on chapter 23. This will be the last lecture for this course. So take good notes and start studying for your final exam. We're talking about amines. Amines are the nitrogen-containing carbons, and the first thing you want to be able to do is classify amines as either primary, secondary, tertiary. So if the nitrogen is bonded to only one carbon and there's two hydrogens, it's a primary amine. If there's only one hydrogen, there's two carbons, it's a secondary amine. And if there's no hydrogens bonded to the nitrogen, it's going to be a tertiary amine. You've been using amines as nucleophiles. So nucleophiles have a lone pair. They are weak nucleophiles because there's no negative charge. The structure of an amine, the hybridization, we count how many things are bonded to the nitrogen. So 1, 2, 3, 4 things. 4 things. So that's sp3. So it is tetrahedral, but less than 109.5 degrees Celsius. This lone pair takes up a lot of space, so it pushes these other groups, these methyl groups, down. They are not considered stereogenic, even though they can have 4 different groups. And the reason why is because they can interconvert at room temperature. Okay, so secondary and tertiary amines that have, so for naming, if they're all the same. So you see that these are all ethyl groups. These are called triethylamine. This is diisopropyl. There's two isopropyl groups, so that's diisopropylamine. This is a common name. So I'm not going to ask you to name amines, but we'll kind of just briefly mention that the IUPAC nomenclature is you find the longest chain. And so here you have 1, 2, 3, right? So that's propane. And then this is coming off of the 2. So there's the 2-amine. Now, since the nitrogen, what's substituted is a methyl. And look at this. This is N-methyl. So we don't have a number. We have an N. So that's an N-methyl for that substituent. Aniline is an important aromatic amine that you need to know. If you have substituted anilines, like this is ortho-bromoaniline. Intermolecular forces of nitrogens, this is the IMF. This determines physical properties such as boiling points and melting points and solubility. If there is a hydrogen bonded to the nitrogen, like this is a primary amine, then they're going to undergo hydrogen bonding, right? So you know that that's pretty high boiling and melting points for hydrogen bonding. Hydrogen bonding is a requirement of a hydrogen bonded to either a nitrogen, oxygen, or a fluorine. You'll see that tertiary amines do not have a hydrogen, so they do not do hydrogen bonding. Since the nitrogen is less electronegative than oxygen, so electronegativity trends increases up a group and across a row. It's less electronegative. The hydrogen bonds are going to be weaker than like an alcohol. So amines are going to have weaker hydrogen bonding than alcohols. So we can see this intermolecular bonding forces and their effects here. If you compare similar molecular weight compounds, we have, this is butanol, and butanol has a boiling point of 118 degrees, and it has hydrogen bonding, intermolecular forces. Nitrogen here, the amine, you can butanamine, butanamine. This has 78 degrees. So even though it has two hydrogen bondings, because oxygen is more electronegative than the nitrogen, the oxygen hydrogen bonding is going to be a stronger. Now look at this one. This one significantly, this is a tertiary amine. This only does dipole-dipole, and it has 38 degrees Celsius for its boiling point, because there's no hydrogen bonded to the nitrogen. Okay, so in your laboratory, you might be doing some IR, infrared spectroscopy, and in your IR, you should be looking around this area here between 3,000 and 4,000 for these NH stretches. And you can see if you have two here, we used to call them the crab claw. They're really kind of pointy. That means that we have a second primary amine because we have two NH peaks. Here, this would be indicative of a secondary amine. And this one, you see, you don't have any peaks. In a Mars spectrum of amines, you're not going to see the NH bond necessarily. It's going to be labile, and that means it's going to interchange with the solvent. It can appear anywhere from 0.5 to 5.0 ppm, so it's hard to know where the exact location would be. Now, amines smell really bad. Okay, they smell really bad. It's not fun to be working in the lab with amines or to have coworkers who work with amines because they smell like trimethylamine. It's like fish protons and the characteristic odor of rotting fish. I mean, look at these names. Putrescine, that's a common name for this diamine. Cadaverine, these are putrid odors. They don't smell well. And we're going to be talking about, the amines are your organic bases. Okay, so when we talk about bases, you probably think, oh, sodium hydroxide and sodium methoxide. And these are compounds that go and take a proton, right? And that's exactly what a base does. But these are sodium hydroxide and sodium methoxide. These typically are considered inorganic bases. Amines are your organic bases, so they too will go and take a proton. So when you're doing an acid-base reaction for your food, sometimes you're given a lemon, and you take that lemon and you put the lemon on your fish. And the reason why you're doing that is you're doing a neutralization reaction. You're actually doing chemistry. Probably did a long time ago when you were a kid, and it tames down that odor by protonating the uh, trimethylamine given off from the rotting fish. Okay, histamine is a triamine. See, there's three nitrogens here. It's a triamine. It's also an aromatic amine. This is a primary amine here. This is present in many of our tissues. It causes physiological effects, symptoms that you get like vasodilation when you're having allergies. So sometimes you can take an antihistamine. This would be that compound. And then we also have Tagamet, which is an anti-ulcer drug. A lot of your drug molecules have nitrogens in them. And I do remember when I transitioned from undergraduate chemistry, and then I did a couple of years of graduate chemistry working on my master's degree. Um, One of the hardest learning curves I had working in the laboratory at Eli Lilly was really learning how to work with nitrogen containing compounds, because every drug molecule seems to have a lot of nitrogens in them. Alkaloids are naturally producing nitrogen containing compounds. So such as nicotine, here's nicotine, which is isolated from tobacco. And so you can see that's what an alkaloid is. Dopamine, you see this is a primary amine here. And dopamine is a neurotransmitter that gets released in your brain cells. You have dopamine receptors. Cocaine is also a nitrogen-containing drug molecule. Amphetamines, they increase the levels of dopamine in the brain to make you feel good. So serotonin, this is our natural neurotransmitter, and it helps with our mood, sleep, and perception, temperature regulation. Fluoxetine is actually Prozac, and that was actually a Lilly drug, and it was first of its class. A first of its class usually makes a lot of money, and it is an SSRI right here, which is a selective serotonin reuptake inhibitor. So when serotonin is released, fluoxetine will go in and block those receptors so it doesn't get reuptake. And so therefore, whatever amount is released of serotonin stays released. General reactivity of amines. Amines, like I said, are basic, and we're going to need to be able to rank the basicity of your amines. So we're gonna do that. That's one of the learning objectives I want you to be able to do, and then we'll get into some reactions. Because basicity and nucleophilicity decrease across a row, nitrogen is the most basic and the most nucleophilic. So fluorine is not nucleophilic and not basic, and oxygen is a weaker base and weaker nucleophile than nitrogen. So they're stronger bases. All right, so the first type of reaction you want to be able to do is an acid-base reaction. And an acid-base reaction, you need to label acid, which is your acidic proton, and then you have a base, and you draw the curved arrows of deprotonation, and then this is your product side. And on your product side, you want to be able to, this is your conjugate acid because the nitrogen has the hydrogen. You want to look up a pKa value. So this is a pKa value of whatever this acid is, and this is the pKa value of the conjugate base, and that'll determine which way the equilibrium arrow goes. It's really not an irreversible arrow. And then we have if it acts as a nucleophile, it's actually attacking, which is typically a carbon. So you've seen that before with a carbon, and you form a new bond. So that's the difference between when nitrogen acts as a base, it's actually going after a proton and deprotonating an acid, and when it's a nucleophile, it's going after a carbon. Okay, so acid-base reactions do happen first and faster because it's so easy to get a proton. And it is an equilibrium arrow. So here we have this, it's showing you that, and if you look at your charts, and I want you to be able to read pKa tables because that's helpful on your exams, you'll make sure you're not looking at an amine. Like an amine, if you look at something like this, just the amine that's not protonated, you're going to see that pKa is around 36. Okay, like ammonia is 36. Be careful because that's not protonated. So protonated is when you have a nitrogen that has 4 bonds to it and it's got a positive charge. Notice that pKa is 10 to 11. So it's as acidic as like a phenol. Remember the phenol? Hydrogens here, those are pKa's around 10. So this proton is more readily acidic than a non-protonated one. So here you're talking, this is a strong acid. You know HCl is a strong acid. You memorized that in Gen Chem. So it has a pKa of less than 0. And so here we draw this here, and you see that the pKa of typically of these protonated nitrogens are around 10 or 11. So let's just call that 11, and let's call that -7. So what's the difference? Well, what's 11 plus 7? 18. There's 18 difference there, so that's 18 zeros. Okay? So if you don't think that that's a big number, then put a $sign in front of it, okay? And then you'll realize that that's how far to the products that equilibrium arrow is lying. Here, this is your typical organic acids. So this is an organic acid, which is a carboxylic acid, right? That's the functional group, carboxylic acid. They have pKa's around 5. And so when you protonate that, that's 11. So you're looking at the equilibrium's about 10,000 times to the product. Okay, so another thing we did a lot when we were making drug molecules, and one of the reasons why you like to have nitrogens is because you can protonate them. So a lot of times we'd take a drug molecule and we would actually take a little bit of gas and we would add HCl gas. And HCl gas would make the HCl salt. You can actually make all kinds of different salts. gosh, we would have lots of just different salts, and you can patent, which is called IP. You can get patents on the different salts because different salts can behave differently in the body. You can have like slower reacting and higher absorptions and stuff like that. Anyway, this is just showing you Benadryl. The nice thing about making a salt, this is water soluble. Once you get a plus minus charge in your molecule, now you have something that's ionic. This is an ionic and it's water soluble. This here is insoluble. Diphenylhydramine is insoluble. And so if you want compounds to be readily absorbed in the blood and transferred through the blood, then they have to be water soluble. All right, so we've talked a little bit about the pK values. I want you to be able to write and draw acid-base reactions with your amines. And so I need to be able to see you label a base and an acid, draw your curved arrows, and then draw your products. And the equilibrium will always lie to the higher pK value. Okay, so we're also going to be able to rank different amines based on their basicity. So we want to look at that. Alkyl groups are electron donating groups. So let's think about this real quick. If you have electron donating groups, those electrons are pushing towards the nitrogen, which makes the lone pair, that's the lone pair that's going to be the basic part that's going to go after the proton, right? So we know that negative is attracted to positive. And so if we have electron donating groups, then we're going to make this lone pair more negative. And when you make that more negative, then it's going to be more basic. And so then the opposite is electron withdrawing groups are going to decrease the basicity of your nitrogen. Okay, it's going to be less basic if it has electron withdrawing groups because it's going to pull the electron density away from the lone pair. All right, so like we have ammonia. Ammonia, NH3, is going to be a weaker base than ethylamine. So this is ethylamine. And why? Because these electron donating groups are going to push the electron density, this is actually an inductive effect, towards that lone pair and make that lone pair more negative. And so here we have, they're showing you the different pK values. Okay, so what about aniline? So if you were going to compare some aniline derivatives, the first thing you want to know is you see here, this is stronger. This is a stronger base. So I want you to know aliphatic amines are always going to be stronger bases than aromatic. Okay. So you see, this is a stronger base because the electron pair is localized on the nitrogen. Here, when you have the benzene, the aromatic, you can delocalize that lone pair. So that lone pair can get delocalized back into the ring, which makes it weaker. So anytime your professors say always, write it down. So aliphatic amines are always going to be stronger bases than the aromatic amines. Okay, since I like to keep everything in pKa values, so the pKa value of methylamine, which is, and when you do pKa values of your amines, be careful because they have to be protonated. Okay, so you have to compare. If you're going to compare them, then they need to be all protonated. Um, so we're comparing these two here of aniline. So you can look up charts on those. Um, or you could look at PKB values. Since you don't have to memorize things, you can look at PKB values. And if it has a lower PKB value, then it's going to be a stronger base. So that's another way. A lot of times if I ask you for the reasoning, I don't want you to tell me because of the pKa or PKB value. I want you to tell me, oh, this is because it's an aliphatic versus an aromatic. So make sure you understand this. Aryl amines, which are what I was talking about, aromatic. So aryl amines are less basic than alkylamines. And alkylamines would be just like the methyl or the dimethylamine. And that's because the electron pair on your aryl amines is delocalized into the ring. Which is the strongest base? Well, these are not protonated. This is an sp3 carbon hydrogen. pKa is 50, not a base. I would think that's your weakest. This is a pKa of 30, about 35 or 36. So these are, you don't even know why that's in there. Let's just compare these three. You don't need pKa values or pKb values. You can look at this and go, okay, these are all three. I bet you this was supposed to be like, this is probably a typo. This is supposed to be like this, okay? And if that was the case, then this would be your most basic, because this would be an alkylamine. So just go ahead and make that correction. These are all aromatic amines or aryl amines. And so this one has an electron donating group. This has nitro as electron withdrawing group. So it's pulling the electron density away. You're caring about this. And this one is nothing, has nothing. So if you had to rank these, the most basic is D, which is the alkyl. And then you would get the most basic. So the most basic then would be A, compound A, where you have the electron donating group. And then you would have C, where you have no electron donating group, but no electron withdrawing group. And then you would have B with the electron withdrawing group as the weakest base. All right, so that's what this is showing you, and you can go over this. If you have a low electron donating group, you're pushing electron density into the ring, which makes this lone pair more basic. And to review electron donating groups, they are compounds that typically have lone pairs, like amines, a hydroxyl group, an ether group, an amide with the nitrogen attached, or a carbon. Electron withdrawing groups pull electron density away from that lone pair on the nitrogen, and these are going to be compounds that, like the nitrogen has a charge, this has a carbonyl group, like carboxylic acids or esters or ketones or aldehydes, halogens, so they're like fluorine and bromine, even though they do have lone pairs, their electronegativity makes them withdrawing groups. The nitrile group. Okay, so rank the following compounds in order of basicity. Well, this has electron donating groups, and it is aryl, not aryl, it's alkyl. So this is an alkylamine. So 2 is going to be the most. And then 1 will be second because ammonia it just doesn't have electron donating groups, but it still doesn't have any delocalization of that lone pair. So we're looking at 2 and 1 here. So A is probably it. And then we have nitrogen in the ring, and then this is a nitrogen outside the ring with an electron donating group. So these, I would probably have to look up the pKb values to know, but well, let's see. So we do have 2 options here. I would have to look up aniline and pyridine, but I'm going to guess aniline, so I would say the 4th, but I would have to look up the pKb values. Let's see if I can do that really quickly. pKb for aniline. And pyridine. Let's see. So pyridine, the pKb value is 8.8. Aniline is 9.4. Okay, so pKb values are like pKa values. The lower the pKb value, the more basic. So 8 is lower than 9, so 3. So make that correction. I was wrong. A is your answer here. Okay, to compare the basicity of an alkylamine and an amide. Okay, amides are not basic. Okay, so just don't even go there. They're not basic. And that's because the lone pair is delocalized into the carbonyl. So it's actually they're more acidic. Amides are actually more acidic, and they will get protonated on that carbonyl oxygen. So they're less basic than amines because the electron pair is delocalized. And that's what it's showing here. It gets protonated. So that's a preferred pathway. And we talked about that with the carboxylic acid derivative. Okay, so this is kind of like, what about the heterocycle, like amines? Well, they're a little bit more challenging because you have to decide, are the lone pairs on the nitrogen available to get a proton? Okay, so that's really the question you're asking. And so going back to here, do you remember that that lone pair would be delocalized in an sp2 orbital? So this has 6 pi electrons. So this is aromatic. Okay. We count those lone pairs on the nitrogen as part of the pi electrons that are delocalized because nitrogen doesn't have a double bond. You remember, if it doesn't have a double bond, then we're going to count that lone pair. So this is not available. So this is not basic. Okay, so pyrrole is not basic. Pyridine, though, however, has a double bond to the nitrogen, So those are at 6 pi electrons. And then these pi electrons are actually in an unhybridized p orbital. And because of that, they are available. So pyrrole is much weaker base than pyridine. Okay, so and this is terms of if you protonate it, then you can look at the pKa values. This is showing you pyrrole is a weaker base, and it actually gets protonated on a carbon. So piperidine is an alkyl amine. It's alkyl. You see it's not aromatic. This is aromatic. So you know that this alkyl amine, piperidine, is going to be more basic. Because I told you always these are going to be more basic. So pyridine is a weaker base than piperidine. So there you can see some different basicity. All right, so these are kind of just some general rules. This might be a nice little chart for you if you needed to print it off or copy it to understand the factors that determine amine basicity. We just talked about them. And then it's kind of nice to have some pKa values of the conjugate acids. Remember, amides are not basic. So these aryl amines or alkyl amines are your most basic. So if that helps when you protonate them to look at those pKa values, these are less basic, the aryl amines. You see the nitro group is electron withdrawing. The methoxy group is electron donating group. So this one's aniline. And then these are your heterocyclic ones. They're even going to be less basic. Okay, so now let's get into some reactions of amines. I can synthesize amines. Okay, so I can synthesize amines. Well, here we are doing an SN2 reaction. This is one of the first reactions that you did, right, in organic 1. And then the nitrogen and H3 is basic, which will deprotonate this. And you'll get this. Now, which one's more basic? Is ammonia? Which one's more basic? Ammonia or propylamine? Well, we just talked about this, right? This has electron donating groups, so this one's more basic. And if it's more basic, it's also going to be more nucleophilic. So guess what? This compound is then going to react with another one of these propyl chlorides in solution. And so then we're going to get another addition. And then you're going to have something like this, and it's going to deprotonate that because you're in a basic solution. And you have this compound, and then this is more basic than both of these. So it's going to react again. So basically you're going to get over-alkylation, okay? You will get over alkylation. And so the problem is this is a tertiary amine. If you deprotonate it, it's a tertiary amine. And it actually goes all the way to the quaternary amine. So if you wanted to make a primary amine, so this would be a primary amine, this does not work. This is bad. Do not do it. If you do this as a way to make amines, which is an SN2 reaction, you will not get credit. Okay, and that's what this is showing you. You have this reaction to get the primary amine, and the primary amine reacts to make a secondary, and the tertiary all the way to the quaternary salt. And that's direct nucleophilic substitution. And so this is polyalkylation when you do it, alkylate over and over and over, and it's just a horrible way to make amines. So we are going to look at other ways to prepare amines. Okay, this is called the Gabriel synthesis. This makes primary amines. And so you can actually buy potassium thiamide, which is this is compound here. You can buy potassium thiamide. It's a nice little salt, and it's a great nucleophile. This is an SN2 reaction where the nitrogen will do an SN2 reaction. And then what happens is you get the nitrogen that adds. I've worked with this molecule. It is really nice to work with. Okay, so you get this. This is an imide. So this is a thiamide. An imide is when you have a carbonyl here and a carbonyl there. So that's an imide. And that's kind of like a protecting group for the primary amine. So when you're ready to release it, you can add hydrazine. This is called hydrazine. And hydrazine is actually rocket fuel. Okay, so you got to be careful not to overheat this. So the structure of hydrazine is actually this compound here, and how hydrazine will dethal and will do a dethalimide. D means to remove, and so anytime you use DE in organic chemistry, it means to remove. So this will go here, this will go up. You don't have to do this mechanism. Then it comes back down, and then it releases the nitrogen. The other nitrogen here will attack this one, and this will go up and then come back down and release the nitrogen. So like I said, you don't have to know this mechanism, but it basically replaces this nitrogen with these two nitrogens. And these are water soluble, so we can just wash it away in the separatory funnel. Remember the separatory funnel? Kind of what you do at the end of every reaction. You got your little separatory funnel. Okay. But then what we care about is that we've made a primary amine. Okay. So we can add whatever alkyl halide, however many carbons, we can add it onto that nitrogen. And it is a primary amine, so that means it has two hydrogens. This is a great way to make primary amines. And so this is the mechanism. This is showing you how to generate your potassium thiamide salt. You don't have to do that because you can actually purchase it, and it's really nice little white solid. Once you have this, you do have a nucleophile and you want to do an SN2 reaction. You typically want to use a methyl or a primary alkyl halide. And then once you do that and you attach your carbon, then you use, it's hydrazine that you use, a little bit stronger than the hydroxide. and you generate your primary amine. Excuse me. All right, so we've already gone through that mechanism. Now, other ways you can prepare primary amines, it's good to know more than one way, is if you have a nitro functional group, you can do a functional group transformation. So lithium aluminum hydride, remember this is a strong reducing agent, and it will reduce the nitro to an amine. So anytime you have a nitro, you can just react that with lithium aluminum hydride, and it will reduce a nitro to amine. That is a functional group transformation. The nitrile will also get reduced with lithium aluminum hydride to a primary amine. Make sure you got your carbon count, 1, 2, 3. The carbon brings in a fourth carbon. Here we have 1, 2, 3. This one we have a fourth. So yes, you can do reductions of nitro and nitrile groups. These are other reagents you can use to reduce a nitro group. Lithium aluminum hydride is good for nitrile. And it's just an SN2 reaction where your negative nucleophile is on the carbon of the nitrile. You can purchase sodium cyanide and you made a new bond, and then you can reduce that to the primary amine. Count your carbons. Here we have 3, 4, 5. 1, 2, 3, 4, 5, 6. So count the carbon in there as your 6th carbon. It is a primary amine. What about secondary and tertiary amines? You can also reduce the amide. Okay, so if you have an amide bond, but you have to use a strong reducing agent. Okay, so you have to use lithium aluminum hydride, and this will reduce that will make a secondary amine. This one here will make a tertiary amine. And so that's what you're seeing here is a primary amide, primary amine, secondary amide, secondary amine, tertiary amide, tertiary amine with lithium aluminum hydride. So which starting material is the best for the reaction below? Do you recognize this as a thal-imide? Do you recognize that this is a primary amine? So we need to do an SN2 reaction with an alkyl halide. So 1, 2, this is your starting material. And that's where this was added. Right? So, and where did the nitrogen come from? Came from here. So the reaction was an SN2 reaction. The bromine leaves. You get this intermediate compound. Here's your nitrogen. And then you got to draw your thal-imide. When you're drawing your mechanisms, make sure you draw your thal-imide. Okay, and then hydrazine, you don't have to actually do that mechanism. You can just go ahead and draw your product. So the answer is D. Another preferred method is reductive amination. Reductive amination is a reaction that if you work in industry making small drug molecules, you'll probably do this at least every other week. Might be doing it weekly. And so your starting material is a carbonyl. So notice this is an aldehyde. This is a ketone. And the first step is you're going to make an amine. Okay? So step one, you make an amine. Remember, this mechanism is nucleophilic acyl addition. Okay? And then once you form the amine, then step two, you use kind of a weaker, not sodium borohydride, you can, but this one is sodium cyanoborohydride. Okay, so see the sodium cyanoborohydride. You use that to reduce the amine to an amine. So let's look at this. Remember, when you make an amine, you lose water. So you don't have to go through that 7-step synthesis that you did before. You can just go ahead and make the oxygen and the 2 hydrogens make the water. And so now you have a double bond nitrogen with the CH3. And that's your amine. And then after step 2, sodium cyanoborohydride, you make in this case, 1, 2, nitrogen has 3 things in one lone pair. You make a primary, secondary amine. Okay, so you see there's the hydrogen. You could also not necessarily include that hydrogen if you didn't want to, but you do want to make sure you do have 1, 2, 3 carbons in your product. Always a good idea to count your carbons, folks. All right, so going on to this one here, you have a ketone. You're going to make an amine because you have a primary amine. You're going to lose water, so the 2 hydrogens going to come from the nitrogen, the oxygen, that's what makes the water. So you're going to have a double bond nitrogen, and then you have this CH3 here bonded to the nitrogen. So that's the amine. And then when you add sodium cyanoborohydride, you're going to reduce that to the amine. And you can count your carbons, 1, 2, 3, 4, 1, 2, 3, 4, and this makes a secondary amine. This is called reductive amination. It's a 2-step method that converts aldehydes and ketones. That's important, folks. Aldehydes and ketones into primary, secondary, and tertiary degree amines. The first step is a nucleophilic attack on the carbonyl group to make an amine, and then reduction makes the amine. Sodium cyanoborohydride is the preferred reducing agent for this reaction. Like I said, this is a very common reaction to do in the laboratory. This makes how amphetamines are made. Okay, so they're just showing you the intermediate is the amine. In this case, you have a secondary amine. So where's the water come from? There's your H, and but it doesn't really matter because then it's going to get reduced with the sodium cyanoborohydride to make a secondary and tertiary amine. Okay, so here we go from, we're going to make a methylamine, and that's how you make methamphetamine. Okay, so propose the best synthesis for the following. So you could choose anything. This is a primary amine. So if you wanted to, you could use the potassium thiamide route for that. So you would do this. This is only for primary amines. So there's your potassium thiamide. And then you got to follow that up with hydrazine. What's the starting material for something like that? So There you go. And that wouldn't be great because that's a secondary alkyl halide. So you might want to make an amine if you were going to make reductive amination, which sometimes I just do RA, then that would need a ketone, and then you would react that with NH3 and then number 2 sodium cyanoborohydride, and that could also work. Okay, so here same thing, you could react it here. This is a primary amine, and then the alkyl halide here for this one would be the benzyl bromide. Or if you were going to do reductive amination here, then this would have to be an aldehyde, right? Because this carbon here, and then you would react with these same reagents. This one's going to need to come from, this is a tertiary amine, so I would choose reductive amination on that, and this carbon here is where my ketone would be, and it's not aromatic. So this one would be definitely reductive amination of a ketone, and the first step would be this nitrogen here, which would be HNCH3CH3, and then you would follow with sodium cyanoborohydride. Okay, so a lot of times we want to do some retrosynthesis. So we look at this compound, this product, and we say, how will we make this? And so you see that you can break the nitrogen-carbon bond, and reductive amination is always great. The starting material, you just got to remember it's either going to be a ketone or an aldehyde. And so here you see that this portion, 1, 2, 3, that carbon has to be the carbonyl, and then this portion is the amine. And that's what they're showing you, that this portion of the carbon before the nitrogen comes from a carbonyl, and then you have to say what's on your amine, and you add the hydrogen, and it's ammonia. This is an aldehyde, or it could be an alkyl group, primary amine, and then you make your amine. You can also make an enamine. An enamine only has 1 hydrogen, but remember you gotta still lose the water, so you're losing the oxygen, but you're also losing a hydrogen from the alpha hydrogen, the alpha carbon, to make a double bond. That's enamine, and these both can get reduced with sodium cyanoborohydride in the next step. All right, so which is the best reagent? Well, you're starting with an aldehyde, so clearly this is that portion, and so you're going to want a CH3H2. This is your CH3NH2, so add the extra H. And then the second thing you're going to want to do, this is a secondary amine, so you don't want to do Gabriel. If you reduce that, it will give you a primary alcohol, so that's not going to work. Obviously, this is not a great reaction because we forgot to add the NH2CH3. So make that correction, and that should be your answer. Okay, reactions of amines with acid derivatives. This is an acid chloride. This is how you're going to make an amide, okay? And so we've done this in previous chapters with our carboxylic acid derivatives, and we know that the ester and the chloride are great leaving groups. So this comes in here, and this mechanism is nucleophilic acyl substitution, and it's how we learned how to make amides. All right, so diazotization. Diazotization. Um, this is good for aromatic compounds. We're going to deal with aniline. Okay, so aniline is our starting material. We're not going to worry about alkyl diazonium salt. So azo is when you have nitrogen, and you see the di is you have two. Now this reagent here, sodium nitrite, NaNO2, makes the this is the NO2, nitrosonium ion. And this, you just got to memorize that this is the reagent. I don't expect you to know this mechanism, but I do want you to convert the amino portion, so the aniline portion, NH2, into the aryl diazonium salt. This is a great leaving group. And so now we're going to be able to do substitution. I think we can come up with maybe 6 or 7 different reagents, and we can make lots of different functional groups. And by this starting material. So I do want you to know these. So here, anytime you have NaNO2 and you add an HCl, this is your reaction mechanism. You don't need to memorize this, and I won't ask you to show it, but it's kind of lengthy. You get a lot of protonation, deprotonation, but I do want you to be able to draw this intermediate. So when you have, I want you to be able to do this. I want you to be able to take an aniline, and I want you to be able to add sodium nitrite and HCl, and then I want you to be able to draw that product, which is the diazonium ion. And that's going to be important, okay? The positive charge is on the nitrogen, because nitrogen gas, 70% of our atmosphere is nitrogen gas. It's the world's best leaving group. Like I said, we're not going to do alkyl because they're not useful. But we do want to do aryl diazonium salts. One of the reasons why we want to do it is because we make a lot of our dyes and compounds. And I don't know if maybe some of you might end up working in FDA or the EPA, and you need to know that these molecules from our clothing and our dyes, they're toxic, and they're going into our wastewater streams, and especially in other countries. So it makes me sad. Okay, and so I think this chemistry is important. Like I say, when you take your aniline compound and you react it with sodium nitrite and HCl, then you get this diazonium compound, and now you can substitute it with different groups, okay? And then you give off nitrogen. So here, it can add an azo compound. So these are all, do you see where your Y is like aniline, different amines, OH? These are going to be ortho pair director. So this is going to be a pair director, and we can couple that. Like I said, nitrogen is a good leaving group. You can add water and you get phenol. Okay, so basically the OH substitutes for the nitrogen. These are the Sandmeyer reactions. If you have a copper chloride or a copper bromide, this is Sandmeyer reactions. and you can replace this nitrogen with a chloride, or you can replace this nitrogen with a bromide. HBF4 is going to replace this leaving group with a fluoride. Sodium iodide or potassium iodide will add the iodide. You don't even need Lewis acids. This is another sand. I call it a sand mire. I guess it's not a sand mire, but it's copper cyanide. And so that replaces the nitrile. So this is a way to convert your anilines into a lot of different functional groups. This will just, hypofluorous acid will just replace it with an H. So it can convert it back to benzene. Okay, so looking at a multi-step sequence that, a lot of times I give you multi-step sequences, so this is something you might want to be aware of. Do you remember we take an aromatic compound and we do a, remember the NO2? So a nitration. So you do the nitration, and then you can reduce that to the aniline. I think we also did like mercury and zinc, HCl, to reduce the nitro. So this reduces it to the aniline, and then we react it with sodium nitrite and HCl, which makes your diazonium salt, and then whatever you want to substitute it with. So like copper cyanide would make a nitrile there, copper chloride, we put a chloride, copper bromide. So you have 6 or 7 different ones. Okay, so what is the best reactant for the reaction below? Well, we're taking benzene. Let me just look at what we have here. And we just did what we just did. You're going to have to do the nitration, right? HNO3 and sulfuric acid. So that's going to make a nitro. And then our next reaction would be to reduce, so we can reduce that with zinc, mercury, and HCl. I think that was one of our go-to reducing reagents. And then we have our aniline. And so once we have our aniline, we can react it with sodium nitrite and HCl, and we can make our diazonium salt, which is the world's best leaving group, and then we can react that with copper chloride, and we'll replace this N2 with Cl. So we got to do 1, and then 3, and then 4. So 1, and then 3, and then 4, and then 5. So we have to do that. But notice we don't have to use a Lewis acid. How's another way we could do that? You all remember, right? Cl2 and aluminum trichloride, or some kind of Lewis acid. Okay, so like I kind of hinted, this is a way to do an azo compound where we can make a dye. So these diazo compounds, it's a nitrogen-nitrogen double bond, and they get into the color spectrum. See the colored? Because you got all these sp2, this is sp2, this is sp2, and then these are sp2. So you have a lot of conjugation, and when you get a lot of conjugation, you get color. So these are our synthetic dyes. So this makes a yellow, like a little butter yellow color with this amine here. Actually, it was once used to color margarine. That's horrifying. Okay, I don't want to be ingesting this. Okay, so here when you have this diazo dye, this comes from the diazonium compound, and then the other portion comes from the electron donor group. And those are electron donating groups that give you the para director. And remember, so this is the mechanism, and then you got your sigma complex and reatomization. And so you can see indigo, blue, the structure for that, purple, Tyrrhenium purple, and this is a bright red color. Also, these compounds and reactions have been used to synthesize sulfa drugs. Sulfa drugs have this sulfur compound. They're good for, so you see how we have this synthetic diazo compound here, was used to kill bacteria. This is actually another terminology you can look up. It's called a prodrug. So this is the molecule that Prontosil is actually stored in, but it releases this to the active anti-biological agent here. And this is the actual active drug molecule. Okay, so which is the best reactant for the following? So you need to recognize that this is a secondary amine. So we're not going to do the Gabriel, so we won't use that. And one thing you could do is you could make an amide. So here you have an amide, and that would give you the leaving group. So you can make an amide, 1, 2, 1, 2. That makes an amide, and then you could do lithium aluminum hydride. So that would work. You wouldn't want to do an SN2 there because you would get polyalkylation. And if you needed to take this carboxylic acid to there, you would have to react that with thionyl chloride. So I would say B is a good reactant that could be reduced to make the secondary amine. Okay, so the other chapter, and you can look at your other chapters, but for your final exam in chapter 27, you also have amino acids. Amino acids are the alpha carbon. So we've talked, and there's the carboxylic acid. So you got a carboxylic acid, that's where the acid comes from. But these are alpha amino acids because you have a nitrogen, an amine, coming off of the alpha carbon. And so all proteins are polyamides. So they're amide bonds, you see, formed by joining amino acids together. And it's this R group that differs, and it gives us different properties. This is called the side chain of the amino acid. And they are stereocenters. So your commonly occurring amino acids are the L amino acids. D amino acids are rarely formed in nature. And so glycine is your only amino acid that is has no stereocenter, because you see that is a methylene, CH2. These also can be abbreviated as a 1-letter or a 3-letter code. They're just showing you that they do rotate plane polarized light, so they are stereogenic. Now, so these are your naturally occurring amino acids. You might want to keep this and look at this chart and be able to classify these different amino acids. Notice that this is a neutral amino acid, which means that this is alanine has a CH3, asparagine has an amide. Cysteine has a thiol, which glutamine, this is an amide. Glycine is just has hydrogen. Isoleucine is just an alkyl group. Leucine is another substituted alkyl group. Methionine is a sulfur ether or a thiol ether. Phenylalanine, just it has an aromatic portion, so that would absorb UV light. Proline is a cyclic secondary amine. Okay, so that's a secondary cyclic amine. Serine is a primary alcohol. You have three alcohol functioning. This is threonine, which is a secondary alcohol. Tyrosine is an aromatic alcohol, like a phenol. Tryptophan is just a cyclic heterocycle. Valine has an alkyl group. And so there's your codes. And so these are neutral. Just pay attention that you have two amides. Okay, so those are amides. I told you you have three alcohols. So you have three alcohols. You have two sulfur-containing amino acids, methionine and cysteine. And you have two aromatic ones, which are tryptophan and phenylalanine. So your acidic amino acids, you have two acidic amino acids. They have carboxylic acid functioning, aspartic acid and glutamic acid. And then you have three basic amino acids. You have asparagine, histidine, and lysine. You see lysine is a primary amine there. On this histidine, which lone pair would be basic? Well, 1, 2, 3, 4, 5, 6. Okay, so those red electron pairs would actually be tied in the aromatic component of the histidine structure. So it would be this nitrogen that would actually be basic. So if you look at proline, isoleucine, and threonine, they also contain stereogenic centers other than just the other stereogenic center, the alpha. Humans can synthesize only 10 of these 20 amino acids. The remaining 10 are called essential amino acids. They must be obtained from the diet. So there's a Zitter ions means that you have a plus and a minus within the same molecule. Okay, so that's a nomenclature thing, Zitter ion. And amino acids can form a plus. They form a plus site by protonating the nitrogen on the alpha carbon, the alpha amino group. And they can form a minus charge by deprotonating the acidic proton. And so you can see the Zitter ion, and the Zitter ion exists at pH 6, so it can get deprotonated and protonated. Now the R groups depend on the structure as to whether they're protonated or deprotonated, and that is only for the basic side chains can be protonated and get positive charges, and then you have two carboxylic acid side chains that can get deprotonated, which can give a negative charge. All right, so we're going to wrap up this. Which amino acid is acidic? So this is your alpha amino acid core, so that's not what we're talking about here. So you need to identify the side chain, and then classify. So this is aliphatic, which would be neutral. This is phenylalanine, which would be neutral. This is alanine, which is neutral. And then this would be your acidic portion, 1, 2, 3. And you'd have to look to see, is that aspartic acid or is that glutamic acid? So you might want to refer to that chart and be able to classify your amino acids. Sometimes it's helpful to put them on index cards according to their what we call the R side chain. And these amino acids will be important in your biochemistry. That wraps up the information you were required for this course.